Recording in progress.
Hello,
Hi.
how are you? How did the quiz go today?
It was just doing a resonance structure of I think it was like a cyclohexane, but with no double bonds, connected to a carbonyl and ethyl. I think I'm not sure if I did it right, but it wasn't too bad.
That's good. And
And
were
then
there
bond line.
bond line? I see.
Mhm.
Any hybridization questions like SP, SP2, SP3, PS?
No, but we're going to get quizzed on that next quiz.
Next quiz. I see. Okay, okay. Um, let's see. So, do you have any questions that you want to start off with?
I think maybe the ones that I kind of sent you,
Mhm.
the ones that we didn't cover from last time.
Yeah, let's see. And let's cover the ones that are not resonance because you just finished that quiz. So let's do like the hybridization ones. Is Newman projection covered on the next quiz?
Oh, sorry.
Is Newman projections covered on the next quiz?
I think so.
I see, I see. Oh, hey Ryan, hey Brooke. Wait, what class are you taking at UC Davis, Brooke? Like, is it Chem 118 A, C, or is it Chem 8A or Chem 8B?
Oh, sorry, I was trying to unmute. I'm in 118C. I'm Camilla's friend.
Oh, Camilla's friend. I see.
Yeah.
Taking with Farhat. I see, I see.
Yes, yeah.
Yeah. Oh, there she is, Camilla. Okay. So hybridization. You had a question of unhybridized bond with s orbitals versus unhybridized with p orbitals. So the atoms that have unhybridized s orbital are going to be the hydrogen atoms.
Okay.
Right. And the atoms with unhybridized p orbitals are the halogens. X, where X could be fluorine, chlorine, bromine, or iodine.
Okay.
Right. So let's analyze these parts. What would be the hybridization of A, atom A?
sp2.
Yeah, sp2. That's right. Because it has three bonding groups. sp2. That's right. Atom L. Let's say it's pointing at this carbon right here.
That would be sp2.
sp2 as well. What about B? Atom B.
You said atom B. Did you say B?
Yeah, atom B.
Oh,
right. What would be
it's
atom B?
sp2.
Yep, sp2 as well. Okay, what about atom C? This nitrogen here.
It would be sp3.
Wait, let me go connect my data. Okay. Yeah, so this is a tricky one. It looks sp3, right? But notice how the pair of electrons on this nitrogen can do resonance with the carbonyl.
So because there's lone pairs, we assume that it's not.
Am I cutting off right now?
Yeah, a little bit.
Okay, let me connect to my other. Hello. How about now?
Yeah. I think it's better.
Okay, it's better now. Okay. So this is a tricky one because this pair of electrons on the nitrogen here can do resonance with the carbonyl. And if it can do resonance with the carbonyl, it's going to be sp2 hybridized. So this is tricky. It looks sp3, but it's actually sp2 because it could do resonance.
Okay.
Mm-hmm. So you have to watch out for the neighboring group, right? Now, what would I be then? What would atom I be?
Would that be sp2?
Yeah, so this one right here, the pair of electrons cannot do any resonance.
Oh, because it's just a single bond.
Yep, it's a single bond attached to 3 sp3 roadblocks. sp3, 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 and then since there's like no sp2 atoms nearby, no resonance able to happen. So that is going to be sp3, right?
Okay.
Whereas this nitrogen here is sp2 because it can do resonance with the sp2 carbon right here.
Right.
Right. What about D?
That would be sp3.
Yep, sp3. What about E?
That would be. Is that just S?
Yeah, so this carbon right here, it has two bonding groups, one single bond and one triple bond. If something has two bonding groups, it's going to be sp,
Mm-hmm.
right? Sp. What about atom F?
The S.
Yeah, S, right? Because hydrogen will have unhybridized s orbital. That's right. That's right. G is like D. It's going to be sp3. What about H?
You said H.
Yeah.
That would be sp3.
Yeah. So halogen, it looks sp3 because there's three bonding groups, but halogens are going to be unhybridized p
Oh,
orbitals,
okay.
right? Like fluorine, chlorine, bromine, or iodine. Mhm. What about J?
Um, would that be unhybridized as well? Oh no, sorry.
So
No, that would
uh-huh.
be sp3.
Yep, sp3. That's right. The unhybridized are going to be the hydrogens and the halogens, right?
Okay.
Hydrogen is unhybridized s orbital. The halogens are going to be unhybridized p orbitals. Oxygens, they are going to be like hybridized, and in this case, this oxygen is sp3 hybridized.
Okay.
Okay, and then K is going to be sp3.
Right.
Right there. Okay. Right. So let's see. Okay, let's move on to 118C. Any questions on 118C? Any practice problems?
I was wondering if we could go over some reactions as well as doing nomenclature for nitro.
Yeah, so the nomenclature for nitrile, I have to like check the notes for that. I'm not familiar with the nomenclature for nitrile, but we could do reactions for like chapter 19, chapter 20. What we could do is like you guys could share your screen for the achieve, and then we could like do like some of the problems there for the problems, right? Um, or like what reactions like do you want to go over specifically, like chapter 19, chapter 20, the carboxylic acid derivative chapters, or the homework on achieve?
Oh, I was thinking like some of the ones that we didn't get to,
Oh, the ones that we didn't get to. Let's see.
if that's okay. If not, it's all
Uh,
good.
wait, let me see. Yeah, there's a lot of them. So I'll try to do one at a time. For the azo halide, that's the most reactive one, right? And I'm gonna go over the concept of why that's the most reactive one. So before we go over the azo halide reactions, let's go over this chart of the carboxylic acid derivatives again. Right. So we have this azo halide. We have this anhydride. We have this ester. We have this amide. And we have a cousin of these derivatives. But before we put that, we have to put carboxylic acid somewhere. And that's going to be between the anhydride and ester, like that. Right. And then the cousin of these derivatives are going to be the nitrile, right? Okay, so carboxylic acid derivatives are going to vary by this leaving group right here, right? The reason why this nitrile is considered a cousin is because it does not have a carbonyl, a carbon double bond oxygen. The reactivity of these carboxylic acid derivatives are going to increase from right to left. Right, the reactivity of the carboxylic acid derivatives. And these derivatives derive from the parent function carboxylic acid. They come from the carboxylic acid functional group. So there's two factors that determine the reactivity ranking, right? Where azo halide is the most reactive derivative, and then azo halide, carboxylic acid and esters are about the same. Ester is more reactive than the amide, and then amide is more reactive than the nitrile, right? Because the nitrile has no carbonyl. So one of the factors that determine this reactivity ranking is going to be the leaving group ability or conjugate base stability. Right. So all of these blue circles here are going to be the leaving groups of the carboxylic acid derivatives. When they leave with a negative charge. So I'm going to draw out those negative charges on those derivatives like this. Right? Where we see the most stable negative charge or the most stable conjugate base is this one with the halogen right here. Because the halogen is the most electronegative atom, so it's better able to hold that negative charge, right? It's the best to hold that negative charge because it's the most electronegative atom. Then we have the anhydride, where the anhydride is going to be more stable, like the negative charge on this carboxyl is going to be more stable than these atoms because this negative charge right here can do resonance with the carbonyl. The OH and OR minus are relatively similar, so that's why they are going to be the same reactivity, right? They are less stable than this one because they cannot do resonance. They are localized. But the negative charge on the oxygen is more stable than the negative charge on the nitrogen because oxygen is more electronegative than nitrogen is. Right. So now that is going to be one factor. But in Fahrenheit's notes, he calls this conjugate base strength, right? So we know that increasing from right to left, that is going to be increasing in conjugate base stability. But do you remember if something is more stable, would it be more or less reactive if something is more stable?
Less reactive?
Yep, less reactive. That's right. So in Fahrenheit's notes, he says something like this. Conjugate base reactivity, right? Where this is the most reactive conjugate base because it's the least stable. He says something like the acer halide is the most reactive, right? Acyl halide is the most reactive derivative because it has the weakest conjugate base, weakest conjugate base, right? Meaning that this X minus is the weakest conjugate base or the most stable conjugate base. I like to think of it like in order of stability instead of reactivity, because the stability makes it more directly proportional, right? Where as we are increasing the reactivity of the carboxylic acid derivatives, we are also increasing in the stability of the conjugate bases, right? So as the conjugate base stability increases, the reactivity of the derivatives also increases. But Fahrenheit uses it the other way. He says the reactivity of the conjugate base instead. So this is the weakest conjugate base, making it the most reactive. So that's like inversely related, right? So that's one of the factors, the leaving group ability or the conjugate base stability. The other factor is going to be electrophilicity on the carbonyl carbon. And there's two factors. There's going to be the inductive or induction factor and resonance. So the acyl halide has the biggest partial positive charge, and the amide will have the smallest partial positive charge because of induction and resonance. This halogen here is the most electronegative, so it's withdrawing electrons or pulling on electrons on this carbon more. So as this carbon is losing electrons, it's becoming more positively charged. This nitrogen is the least electronegative, so it has the weakest pull, making it the smallest partial positive charge. And then oxygen is in the middle, so it's in the intermediate, making it the in the middle, right? The middle partial positive charge. So that's the induction effect. The resonance effect is gonna be like this, right? Where halogen, like we said earlier, is the most electronegative atom, so it does not really want to do resonance with that carbonyl. It does not want to donate its electrons to that carbonyl. It does not want to give it negative charge. So that maintains that big positive charge right there. Whereas if we look at nitrogen right here, this nitrogen is going to be like the least electronegative compared to oxygen and halogen. So it's the most willing to donate electrons into the carbonyl, giving it more negative charge, right? Because it's donating electrons, which are negatively charged. And as this carbon is gaining negative charge, it's losing positive charge, which is why it has the smallest positive charge, making it the least reactive derivative, right? So the positive charge on the carbonyl-carbon is dependent on the induction effect and the resonance effect. Right, so that's what the other factor that determines the reactivity of these derivatives. But I like to think about the reactivity in terms of the conjugate base stability or leaving group stability ability. Right, the better the leaving group ability, the more reactive it is. Right, the better it can hold the negative charge. Right, so that's the theory behind most of these reactions that you will see in chapter 20 and 19. Right. Okay. So the acyl halide will be the one that can do the most reactions because it is the most reactive. Right. So let's say we have this acyl halide right here. We can do hydrolysis by adding neutral water, which would convert that acyl halide back into the carboxylic acid. We can convert this acyl halide into an anhydride by adding a carboxylate. Right? Where this carboxylate will be the nucleophile that attacks that carbonyl carbon and go through with the whole mechanism. We can convert this acyl halide into an ester by adding neutral alcohol. We can convert this acyl halide into an amide by using at least 2 equivalent of amine. Or you could use 1 equivalent of amine in some kind of base like pyridine. Let me just say pyridine, EYR. Right? And that will convert that into an amide. We can reduce this acyl halide using LiAlH4 or NaBH4 and acid workup, which would reduce that acyl halide into an alcohol. Right, so that's the reduction. We can do an organometallic reagent like RMGBr or Li acid workup, and that's going to add it 2 times, right? Or group 2 times. We can do this bulky reducing agent, lithium, aluminum, butoxide 3, second step, H3O plus, to reduce it into an aldehyde, and it stops at the aldehyde. It won't go all the way to the alcohol. Right. Let's see what else. This like chart right here will basically summarize the chapter 19 and 20 reactions here. So let me back here, paste. This is like the reaction list. Right now, I was going over the acid halide or acyl halide reactions. So we got the carboxylate, which makes the anhydride. We got water, which does hydrolysis. We got alcohol, which makes the amide. We got the amine, which makes the amide. I mean, yeah, the alcohol makes the ester. The amine makes the amide. We got the strong organometallic Grignard reagent, LiLH4, that one, NaBH4. Okay, and we have the weaker one as well, the R2-CuLi, the organocuprate. Right. If we use an organocuprate, that's going to only add the R group once, right? So it's going to stop at the ketone there. So we see that because acid halide is the most reactive derivative, right? So increasing from right to left is increasing in reactivity of the derivatives, reactivity. And that's why we see in acyl halide, they have the most amount of reactions that it could do. And it decreases as it goes on to the less reactive derivative. Like that, right? And then these are the reagents that you need to be familiar with there. Right. Okay. Are there any specific reactions that you want me to go over the mechanism of for this acyl halide big flow chart of reactions?
I don't really have any like specific ones in mind yet.
Oh, shoot. Okay, okay. If there's any like homework problems that you come across, or anything, we could like also like do it one by one as well, for a while, and then we could do that as well, and then move on from there. Right. Uh-huh. Uh-huh. Yeah. So yeah, because like all of these here would be majority of the reactions, as like you go down the reactivity table, then like they're able to do less and less reactions. Okay. Let's go back to 118A. Elysia, do you have any practice problems that you wanted to go over, or any specific questions?
Let me see real quick. Oh yeah, there was one. I'm not sure if it listed. Oh, that one. Yeah. I was a bit confused with eclipse staggered. That's kind of what we learned last lecture, but I was just a bit confused.
About the differences between eclipse, staggered, gauche, and anti.
Yeah, and then like determining high and low energy.
High and low energy. Right, right. Okay. So this is talk about Newman projections. And Newman projections is a way of rearing a molecule. So let's say we have a random molecule like this, like that. Let's say you're gonna have like your eyes right here, and this is like you right here. And then you're looking down at the molecule like this. This is your vision right here. So you're looking directly at that carbon right there. Right? So that's the first carbon you see. That's going to be represented by this dot right here. You do not see this bond behind it. That bond is invisible to you, right? It's right behind that carbon, so you can't see that. But you do see the groups behind it, right? Because they're like sticking out. So the carbon behind it is going to be represented by a circle, a big circle, like that. Right? Oh my God, like this one right here. This big circle right here is that carbon right there on the back. Right? This point in the front is that first carbon that you directly see. I'm gonna draw out the invisible hydrogen, like that. So we see that there's 3 other groups attached to this first carbon besides this back carbon group, right? And those 3 other groups are the tert-butyl group, the ethyl group, and the hydrogen group right there. I'm gonna draw those 3 groups out like this. Tert-butyl up here, ethyl down there, hydrogen down there. Right. Now, if we look at the back carbon, this back carbon here is attached to 3 groups as well. An ethyl group, methyl group, and hydrogen. I'm gonna draw it in this form, and then I'll show you like the rotations and what these conformations mean. I'm gonna draw the ethyl group down here, methyl group right here, and then the hydrogen right here. Okay. So notice how all the groups are like as far away from each other as possible. Like it's 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees. If they are as far away from each other as possible, we call this staggered. Right, staggered conformation. And there's 2 types of staggered conformations that you need to know, 2 specific types. There's the anti-staggered, and there's the gauche staggered. Okay, so to determine which one we have, look at the first carbon here. Ignoring the back carbon groups, what's the bulkiest group out of the 3?
The T-butyl.
Yep, T-butyl or tert-butyl is the bulkiest group. That's right. and I'm going to circle that in red because we're going to keep track of the bulkiest groups of the first carbon and the back carbon. Now let's look at the back carbon. Ignore the first groups. What's the bulkiest group?
The ethyl?
Yep, the ethyl. That's right. Okay, so if we go down here and I circle the bulky group of the first carbon and the bulky group of the back carbon, notice how they are anti to each other, 180 degrees apart from each other.
Mm-hmm.
This is what we call an anti-conformation, right? And think of that because of this thing called steric hindrance. This is when you learn about the term steric hindrance. Have you come across that term yet, steric hindrance?
I don't think so.
Let's see. So steric hindrance, you could think of it as like the portions of the molecule bumping into each other. So like if the groups are close to each other, like the big methyl groups, carbon groups, hydrogens close to each other and they like touch each other, that's steric hindrance, right? If you have like very bulky groups here, very bulky groups here, and like a lot of bulky groups everywhere, like it's gonna be very crowded, and they're gonna touch each other. That's steric hindrance, and that's not like stable. That's unstable.
Okay.
Right. If you have more steric hindrance, you have less stability. You are less stable. Right? And vice versa. We want to avoid steric hindrance. We want like to have space. Right. So anti right here has the least steric hindrance.
Okay.
And if it has the least steric hindrance, would it have the most stability or the least stability?
Most.
Yes, most stability, because steric hindrance and stability are inversely related. Now, if it has the most stability, would it be the most energetic or the least energetic? Would it have the highest energy or the lowest energy?
It would have high energy.
Yes, highest energy, right? Highest energy. Because stability and energy are inversely related.
Mm-hmm.
So now I'm gonna rotate the groups 60 degrees, right? The back carbon groups. If I do that, keep the front groups the same. So those groups stay the same. In the back carbon, we have 3 groups. I'm gonna rotate it like this. Boom. Whoa, whoa, whoa. Boom. And boom. Right. Now notice how they are like on top of each other, like 0 degrees apart of each other from each other. This is what we call the eclipse. They're eclipsing each other. Eclipse conformation.
Okay.
Right. That introduces torsional strain. Torsional strain. Right. Because the bond angle is very weird. Like they don't want to be in that bond angle. It's very like strained.
Mm-hmm.
Yeah, very strained. It has that torsional strain. Okay. Let's rotate it 60 degrees one more time. Keep the front groups the same. Rotate the back groups 60 degrees. Boom, boom, and boom. Does that make sense so far? Right, like on like how I got to this group right here. When I'm rotating the groups right here, I'm keeping the front groups the same, and I'm just rotating the back groups 60 degrees one at a time. Right. This ethyl group here, like rotate 60 degrees, so it's now there. Hydrogen is now here. Methyl is now here. If I rotate it 60 degrees one more time, now the ethyl group is here. The hydrogen is here. And this should be methyl. And the methyl is here.
Mm-hmm.
Right. Okay, so now we are back in the staggered conformation. Okay. Now I'm gonna circle the bulkiest group one more time of the front carbon, the terbidyl, and the bulkiest group of the back carbon one more time, which is the ethyl. So notice how they are like very close to each other. Like they're not directly on top of each other like eclipse, but they're close to each other. They're introducing steric hindrance, right? So this is gonna be the gauche conformation. Gauche conformation, right? Which has steric hindrance. They're like bumping into each other now. Right. Okay. So that means that this would be less stable than this one right here, making that have or when I asked you the stability here, wait, did you say lowest or highest energy? Like if this was the most stable?
Low.
Low, yeah. It's supposed to be lowest. Yeah, it's supposed to be lowest. Right. Lowest energy. That's right. This one here would be considered less stable because of less steric hindrance, meaning that it will have higher energy compared to this one right here. Right. But eclipse would be less stable, like the least stable. Eclipse is the least stable because it has like torsional strain and steric hindrance, you could say. Yeah. So that's Newman projections, like how you could view them, how you rotate the bonds to get the different conformations, like staggered, eclipse, and then the two different specific types of staggered, anti and gauche. Right? Anti is when the two bulkiest groups are on an opposite side of each other, anti to each other, and gauche is when they are adjacent to each other, but still staggered, like that.
Okay.
Uh-huh.
And you said that was eclipse that you're referring to?
This is eclipse right here.
Yeah.
Right, yeah, that's eclipse, where the groups are on top of each other, eclipsing each other, 0 degrees from each other. Right?
Okay.
And that introduces torsional strain. Gauche has steric hindrance where the bulky groups are close to each other, so they're bumping into each other. That's called steric hindrance. Right? That decreases the stability and increases the energy, right? Because lower stability, higher energy.
Okay.
Uh-huh. Yeah. So try practice problems based on what we went over here, and let's move back to 118C.
Okay. Thank you.
Yeah. Okay. Let's see. Let's try to think of some specific problems here. Oh yeah, I think we went over the reduction reactions. We went over the.
Oh, I sent you some achieve homework.
Oh yeah. Let me go check that.
Oh, okay. They're kind of long though.
Oh shoot.
Yeah.
Let's see.
So
Let's check it out.
if it's not possible.
Let's see. This one. Oh shoot. Okay, let's do this one. This is one question. These 8 steps. Okay. So for the first question you sent, let's see what this is asking. Let's see. Okay. Step 1. Add curved arrows. And what they gave is this Lewis structure of hydronium ion with a positive charge and this alcohol with this carboxylic acid. Okay. So this is testing a acid-base reaction. We know we have a strong acid because of the strong acid H3O plus here. Whenever we have a strong acid, we always have to look out for the strongest base that we can react with the strong acid, right? So which oxygen atom do you think is going to be the most basic oxygen atom that can get protonated, that can grab that can grab one of these hydrogens right here?
The carbonyl
Yeah,
oxide.
the carbonyl oxygen is the most basic because when we protonate it, we're gonna get this conjugate acid here. Right? Where this conjugate acid can do resonance with the hydroxy oxygen like that. Whereas if you were to protonate the hydroxy oxygen instead, the conjugate acid would not be able to do resonance like that, right? But this carbonyl oxygen, once it gets protonated to form this conjugate acid, it can do resonance like this, making it more stable, which makes this carbonyl oxygen the most basic. So that's step 1. Step 2, complete the structure and add a curved arrow. Draw only one curved arrow. Okay, so they give us water and this molecule here. This is also testing acid-base reaction, but now the water is going to be our base, right? The oxygen is going to get protonated by, would it be the alcohol hydrogen here, or would it be the carboxylic acid hydrogen here? Which one is the stronger acid?
Carboxylic acid.
Yeah. So we would draw the arrows like this and give that oxygen a pair of electrons to give us this conjugate base. The reason why the carboxylic acid, yeah, do you know the reason why the carboxylic acid hydrogen is more acidic than the alcohol hydrogen?
Resonance, the oxygen, I have no idea.
Yeah, the conjugate base of the carboxylate can do resonance. So it falls back to resonance. Like everything falls back to resonance, and okay, like it shows up in monocyte A, B, and C. When you deprotonate it with the negative charge here, it could do resonance. Whereas if you like deprotonated the alcohol hydrogen, this oxygen with the negative charge cannot do resonance because of this sp3 roadblock. That's right. So that's the end of the second step or second part. Let's move on to the third one. Complete the structure and add the curved arrows. Omit H2O. Wait, is that iodine or hydrogen? Oh, I think that's H. Yes. Oh, H.
Sorry, the photo that I sent you was kind of cropped, but the oxygen at the lower right is attached to a hydrogen. Yeah, you got that. Okay.
Yeah, a hydrogen. And is this the molecule that you drew on the box, or did they give you this molecule on the box?
They gave it.
Oh, they gave this molecule on the
All of
box?
the ones that I sent you are the ones like the thing.
That they gave it and you didn't like touch anything of it.
Yeah, no.
That's true.
How you do the electron pushing like on this? Yeah, I don't know.
Yeah, because this one. Wait, is this an OH as well? The bottom left oxygen.
Yes.
Okay, so there's 3 alcohols here.
Yeah.
Mm. Reacting with wait. One, two, three, two, three. 1, 2, 3, 4. Oh, okay. So since they gave us the product, which is this 5-membered ring, and water as a side product. And they give us, yep, that one. This structure is not complete. In order to make it complete, we have to make a double bond right there and give this oxygen a positive charge. The reason why I did that is because I want to make this carbon my electrophile. So I'm going to dot that carbon right there. And the reason why I want that carbon to be my electrophile is because I want this carbon here to be my electrophile. I see that I made a 5-membered ring where I'm going to say that this oxygen here was my nucleophile, which is this oxygen that made a new bond right there. This is the new bond that gets formed between the star and the dot. And when that happens, right, like when this intramolecular reaction happens, we form a 1, 2, 3, 4, 5-membered ring, where the first atom of the 5-membered ring is the oxygen atom right there. So when this oxygen atom attacks this electrophile and pops the double bond back into the oxygen, we get this resulting product here, right? This geminodiol.
Just to clarify, without the double
Mhm.
bond, it wouldn't be an intramolecular.
Yeah, without the double bond, then this could not happen, right? Like if that was just an alcohol, like it would not do anything, no reaction,
Okay.
right? We had to put that double bond right there, and think of it as an activated electrophile, right? Like this is a protonated carboxylic acid, which makes this an activated electrophile on the carbonyl-carbon of the carboxylic acid, right? Because you know how when we did fischer esterification or trans-esterification, the first step of those in acidic conditions is to protonate the carbonyl oxygen in order to activate the electrophile. This is the activated electrophile already right there, right? Which then allows this weak nucleophile to attack. But in this case, this turns out to be an intramolecular reaction because the nucleophile is on the same molecule as the electrophile, right? So the molecule is attacking itself. One part of the molecule is attacking itself. And in all intramolecular reactions, we form a ring, which is that ring right there. Right? If this was a mechanism thing, this oxygen will have a hydrogen, positive charge, and then something would deprotonate it. Like let's say OH minus or water would deprotonate it, giving us that final product that they give us already. Right. But let's see what the next part is asking for. Add curved arrows. Oh yeah, they did give that hydrogen with a positive charge as well. So this is the direct result after this intramolecular reaction, right? Where this oxygen right here, the starred oxygen, is still attached to its hydrogen, right? And because it has 3 bonds, it will have a positive charge like that. Now they give us water to draw the curved arrows. That water is going to deprotonate the positively charged oxygen, right? And that's probably going to be the next box. Yep, it is, which is this one right here. OH, OH. Okay. Okay. And then they also give us the, okay. Yeah, I see what they're trying to do with this problem, but the word that it's asked is so weird. I'll show you what they were trying to like test, like what reaction they were trying to test for this problem here. After I finish up this problem. Let's see. Was that arrow like drawn there already? Yeah, I think you're so right. Like since you said like everything like that's drawn is like given to you.
Yeah.
Since that, that's good. That's good. Okay, so that arrow was already there. Water is here already here. Okay. They give us hydronium ion, strong acid. This is the protonate, the group you want to kick out, deprotonate, the group that you want to keep part, right? Or since they already give us like what we want this oxygen right here to be protonated. So the arrows of that would be like this. This oxygen here would attack that hydrogen of the hydronium ion and kick out that conjugate base right there. Right. That's going to give us this incomplete structure, right? Because this oxygen right here that just gained a hydrogen bond is going to now have 3 bonds, 1, 2, 3. So it should have a positive charge, right? Now, looking at the next box, I know that this is the 2-step driving force reaction, where once we have the good leaving group primed to drive this good leaving group to leave, we're going to reform the carbonyl or form the carbonyl from this oxygen and kick out this leaving group at the same time. And that's going to give us the next box, almost. Yeah, because it is not complete. Yeah.
What is it?
Yeah. Sorry, what was the question?
Just to clarify, the way we know what the leaving group is water is predominantly the leaving group, or is it because it's just charged?
Right now it is charged, so it makes it the binding group, right? Because when it leaves with a -1 charge, so it's gonna leave as a neutral molecule.
Wait, sorry, you cut out a little. Can you say that one more time?
Yeah. So we know that this is a good leaving group because it's positively charged. Right.
Okay.
A proteinated oxygen with a positive charge is a good leaving group because when it leaves with a -1 charge. So +1 -1 is a charge of 0, and it leaves as a neutral molecule, which is stable. Right.
Okay. Thank you.
Yeah. So now after that, we're going to have this that they gave us, but this is not complete, right? Because this oxygen here that just made that carbonyl is bonded to a hydrogen, which is that hydrogen right there, as a positive. So it's a bonds. And then they wanted you to draw arrows of this deprotonating step to neutralize the carbonyl oxygen, like that, right? Step 8, complete the structure. All right. That is complete. Let me see. Okay, let's go back from the first thing. Okay, so carboxylic acid gets protonated to form this activated electrophile. And then from here, like I didn't know what they were trying to do, but then I see what they're trying to do now. They're trying to show you the mechanism of this intramolecular Fischer esterification problem. We have this where the next step here. Already, hold on. OH2 plus. Yeah. So since I know what they're asking for now, I'm gonna go back and make sure it makes sense with everything. Add curved arrows, protonate the carbonyl oxygen, complete the structure. This wasn't complete. Second one, because this is supposed to be protonated after the first step. Water. Okay. Draw only one curved arrow. And add a curved arrow. Draw only one curved arrow. Okay. So that's not there. That's going to be complete the structure. What is it? Complete the structure and add a curved arrow. Draw only one curved arrow. So after you protonate the carbonyl oxygen, it gets protonated. Positive charge, yes. Here, do this thing right here. Oh, resonance. Resonance. I see that double-headed arrow. Okay, they wanted you to draw resonance here. So that is going to be like this. Only one curved arrow. Okay, I see. So you will draw one curved arrow, draw the double bond, draw only one arrow from the double bond to the oxygen. And the resonance structure of that is going to be a neutral oxygen and a positively charged carbon there. And there should be brackets here to show that these two are resonance structures from box 2 and box 3. Right? And then box 3 right here, to draw the complete structure, this is what it would look like. Right? Box 3 is going to be that resonance structure. Draw carbon here a positive charge to make it complete, to make that electrophile. And then when we draw curved arrows, we draw this out attacking that positive charge, which leads to this box 4, which gets deprotonated. And then this is box 5, add curved arrows. This is deprotonate that to get to box 6, complete positive charge there. Box 7, reform carbonyl, kick that out. The structure and add curved arrows. Yeah, positive charge. Yeah, the last this the water would deprotonate that oxygen. So try setting this here. So these two curved arrows. H3O plus. Like my notability isn't catching up to the Zoom. Okay. So yeah, let me know when you finish drawing these two arrows for box 1.
Yes.
Okay. For box 2, draw this one curved arrow from the carbonyl, the double bond, to the oxygen. Just that one arrow. Just that one curved arrow right there. And let me know when you're ready to move on to box 3.
Okay.
Oh, and then for box 2, also put a bond to hydrogen, to that carbonyl oxygen, and give that oxygen a positive charge. Right? It's missing that on the box right now. Right. Let me know when you also added this hydrogen and the positive charge. on that
Yeah.
oxygen. Okay. So box 3. For box 3, put a positive charge on this carbon right here.
Okay.
And also for box 3, draw this curved arrow from this oxygen to that positive charge on the carbon right there.
Okay.
Okay. Now for box 4, the curved arrows would be this deprotonation step. The water is going to deprotonate this positively charged oxygen. Right. So there's 2 curved arrows from this water oxygen to this hydrogen, and then the bond between that hydrogen and oxygen is going to go onto the positively charged oxygen right there.
Okay.
Okay. For box 5, curved arrows. Box 5. The curved arrows are going to be protonating this OH with the H3O plus strong acid right there. So draw an arrow from this oxygen to this hydrogen and kicking out that water. Right.
Okay.
Okay. Now for the next box, give this oxygen a positive charge, the oxygen with 3 bonds. And then add this extra arrow from this bond to the oxygen.
Okay.
Okay, box 4, box 5, yep. Okay. Now the last one, use the water to deprotonate. Oh wait, give this carbonyl oxygen a positive charge and a hydrogen bond, and then deprotonate it with the water that's given around in an environment. So 4 things to add: a bond to hydrogen, a positive charge on that oxygen, and these 2 curved arrows on that box.
Okay.
Uh-huh. And that should give you the final product where it should be complete. So try, wait, have you tried it in attempt? How many attempts do you have for this problem?
5,
this
but
5?
we have the same problems.
Oh,
Everybody has the same problems.
everyone has the same problems?
Yeah.
Okay. Have you tried it, an attempt for this type of problem yet?
Not yet.
Okay.
Not this one.
Let's try submitting it. If it's wrong, then don't try anything else. I'll try to see like what's the little small detail that we're missing, and then I'll get back to you. I'll text you. But try submitting it for now.
Oh yeah, it's incorrect.
Oh, it's incorrect. Did it say like which box is incorrect, or did it just say incorrect?
All of them. Wait, they're all red. Yeah, I don't
They're
know.
all red. What?
Um,
What?
it's missing non-binding electron pairs.
Any feedback? Like, what's it saying?
Yeah, that we're missing non-binding electron pairs. I'll send you a photo.
Oh, like these ones here. Oh, they want that in there too. What?
Oh, really? Okay. Well.
Yeah, that's what non-binding electrons mean. So, they want you to include those out explicitly. Oh, like like all the carbonyl oxygens of the boxes, they're, you know how they didn't show any like non-binding electrons? Like for this one, there's 1 non-binding electron right there. But we just assume that it's there. But they wanted us to draw that there, right?
Okay.
So this
I'll
program is very specific, very nitpicky.
yeah. Thank
Right.
you. I appreciate it.
Yeah, no problem. I'll get back to you on that and send me the whole instructions too, like what was above the boxes. So I read like what they want specifically.
Oh yeah, no
Uh-huh.
worries.
Yeah. But what they were trying to test you was the intramolecular fischer esterification reaction and mechanism. And they try to be sneaky. They try to add a resonance structure in there, right? Which is the electrophilic carbonyl-carbon.
And the way we know this is because there was an acid and a base.
There is just an acid. We're in acidic conditions. We are not in basic conditions. Like everything here is in acidic conditions.
So if everything's an acid or acidic conditions, then we immediately think Fischer esterification.
As long as the reactant that you have is a carboxylic acid, you have alcohol somewhere, you have acid, and you're creating an ester. Right? This is the general reaction of Fischer esterification. You're creating an ester from a carboxylic acid, but make sure you have your alcohol somewhere.
Okay.
Right? If your alcohol is within the same molecule as the carboxylic acid, it's intramolecular. So intramolecular, if the alcohol is on the same molecule as the carboxylic acid. If not, if it's outside, it's intermolecular. Right. In this case, they give us an intramolecular Fischer esterification because they give us an alcohol on the same molecule as the carboxylic acid. Right. So this alcohol here, this carboxylic acid here, and this acid shows that this was a Fischer esterification reaction.
Okay. Thank you.
Yeah, no problem. Okay. Elysia, do you have any last minute problems that you want to try before we end the session?
I did just want to get I just wanted to check on my answers for I think it was like the condensed formula. I wasn't sure if I was doing those right, but I had my answers already down.
Yeah. Is it on? Yeah, I don't think it's on this one, right? Is it on Discord or?
It should have been with that one. It would have been like under question 2. I think I labeled it on one of those pages.
Oh, right. I think it's. Oh, right here. Yes.
Yeah.
2. Oh, right here. Okay.
And then I kind of like did my reasoning or like questioning as to why.
Yeah. Oh, I see right here. There you go.
Yeah.
Organized. Yeah. Cho. Double bond. Oxygen. Hydrogen, same carbon. Right. Cho. Aldehyde. Cho. Right. This is the central carbon right there.
Mm-hmm.
That central carbon is attached to 2 methyl groups as a bridge. So we put parentheses that like combine these 2 together to give you CH3. Let me make this smaller. Like parentheses, CH3, 2C, like that.
Okay.
And then that has a CH, right? Because there's one invisible hydrogen there. That's right. And then CH2, that's right. CH, that's right. CH, Br with the parentheses, that's good. CH2. Yep. And then Cho. Yeah.
Okay.
Right. So the only thing would be like the branches here.
Okay.
Right. Okay. So the next one, B. Question mark.
Yeah.
Butyl, that's right. How do you write this in condensed formula? CH3, CH2, CH2, COO, right? And now this is the tert butyl. So This is the central atom right there, the one that I just dotted in red.
Mm.
And I'm gonna put a C right there. How many branches is that? Like, how many branches does that central carbon have?
Um, would that be 3?
Yes, 3 methyl groups. So parentheses, CH3, parentheses, 3.
Oh, okay.
Uh-huh. Yeah. COO, which is the COO. And this central atom C right here is that central atom. And then we
Mhm.
put parentheses to show the 3 branches, the 3 methyl groups. Okay.
Okay, okay.
Yeah. Okay, next one. Ethyl branch to carbon. Is subscript allowed here? Yes, the subscript is allowed here.
Okay.
CH3, CH2, CH, CH3, CO, CH, right. Okay. What? what? Where did this come from?
Uh, I think I may have tried to show that was like an ethyl.
Oh, ethyl, CH, CH3, CO, CH. That's right. And then this is the ethyl right here, the one that you put afterwards.
Yeah.
And there's 2 of them, so we put that in the parentheses like that, and 2 like that. Because right now, what you drew right here, it looks like this. Oh no, that wouldn't make sense because how would that hydrogen have a hydrogen? How would that carbon have a hydrogen? It would be like this, and then boom, boom, like that. Right. It looks like you have 2 methyl
Okay.
groups coming out like that.
Okay. Whoops. Okay, thank you.
Yeah. And this is how you would draw the 2 ethyl groups as a group, as a branch like that.
Right. Mm.
Really confused on how to condense this. So same thing. We have the central atom here attached to 2 ethyl groups. But this time we're starting with CH3, CH2 because it's at the left side, right?
Right.
The left side has the CH3s like that. And there's 2 of them, and then that's the CH right here. Right, where this is the central atom like that. Right.
Oh, okay, I see it.
Right. Like this is the one ethyl group, this is the other ethyl group on this central atom right there. The next is an alkyne, so we put CC. And then I think you got the rest, right? Like CH, let's see, 1, 2, 3, 4. So that's at least 3. So we could do CH2, 4, and then OH. Or you could put CH2, 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 OH. That's also acceptable.
Okay.
Right. But keep in
But
mind,
since it's more than 2, then it's okay to have it as 4.
yes, that's right. It has to be more than 2.
Right, per
At
parentheses.
least 3. At least 3.
Oh, for chain.
For the parentheses chain, yeah. The CH
Okay, that's
more than 2. At least 3. Did I name this right? Let's see. CH3, CH2, CH, 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 CH2, CH3, CH, Cl, CH2, C. Don't put apprentice. Oh, yeah. For amides, don't put apprentices. Actually, I think this is optional, but yeah. Yeah, I think that's fine. That's fine. CO, NH. Yeah, you got it.
okay. Because in class we learned that either we can just we can somehow draw like a double bond on top of that carbon to say like there's an oxygen, like a carbonyl, or we
Yeah.
can put it in parentheses.
Yeah, and they said it's optional, right? Like you can do either or way. Like
Yeah, either or.
that's good. Yeah. Because I usually see it like without the parentheses, but I realized that this is optional, so you could have done it like this as well, if that makes more sense for you.
Yeah, because I know I would think that if there didn't have a parentheses, then it would just be like a
CONH.
like it would just be like it would be part of the chain instead of like branching out of from that carbon.
Oh, yeah. That makes sense. Like the parenthesis is like branching out, which it is branching out, like the carbonate.
Yeah,
do
so
that.
like so are you saying
Uh-huh.
that people also like they add it without the parentheses?
Yeah, I see it like this a lot.
Oh,
Uh-huh.
okay.
Yeah.
But that would be okay as well.
Yeah, this will be okay as well.
Okay.
Yeah. And
Thank
I've
you.
seen it in like this more more often than this form right here.
Mm-hmm.
Uh-huh.
Okay, that makes sense. Thank you so much.
Uh-huh. No problem, Lucia. Good luck. When is your next quiz? Is it this week or next week?
I think it's next week, yeah.
Next week, I see. Yeah. And thank you for like doing all these like explanations, like what you think, and then asking questions
Yeah,
on the
thank
test. Like
you.
it's so organized.
Yeah, thank you for getting or helping me with this even though like time has passed, but
Uh-huh. Yeah, no problem. Yep.
thank you. Have a good night.
You too. Good night. Hey Ryan,
Hello.
tired?
Finals are 2 days from now. Wait, actually, yeah, Thursday, Friday.
Thursday,
But
Friday.
it's like first period, fourth period, and then third period is Thursday. Second and first is Friday. Hmm. Busy day. I can't hear you.
Oh shoot. Hello. Can you hear me now?
Yeah.
Hello. Oh yeah. It's been a busy day. It's been so long. Like yeah. Like woke up early, took some naps in between, like in class nap room. Tutored for like how many hours today? 1, 2, 3, 4 hours today, and I gotta study for a quiz this Friday soon. So it's been long.
Uh, yeah, I feel like I can take a nap, but I've like slept at like I slept yesterday. Slept at 3, 4 in the morning, and I woke up at like 5:30, and then and then like in my fourth period, I was about to fall asleep, but I had an assignment to do, so I just literally took away my chair and I just started crouching while doing my homework for that class. It was in the corner, so like no one really saw me crouching. Also, you're lagging out. Oh, it's fine now.
Oh shoot. Hello.
Yeah, hello.
Okay. Yeah. What time did you sleep? Last night. I think you cut off at that part.
Oh, dang. Uh, wait, I'm gonna leave first.
Okay.
Hello?
Hello.
Dang, you are tired.
I'm so tired.
uh,
Yeah.
Yeah, so basically today I think wait, I can just check my search history because like that's like the last time I ever. Okay. So I went to sleep at like 3:30 last night, and then I woke up at 6 o'clock. Actually not 6, but more like 5:30 ish. So that'd be like 2 hours of sleep.
3:30 to 5:30. Oh my god, I had 2 hours of sleep like last night too. Actually.
Oh damn. What
Dang.
time
Like
did you go to sleep?
I went to sleep at 2:30. Woke up at 4:30.
Ooh, I went to sleep at 3:30, woke up at 5:30.
Oh my god, so like an hour after me. And then you slept an hour after me, you woke up an hour after me, but we had the same amount of sleep. That's crazy. What a
I'm turning into
coincidence.
you. No.
Oh my god. What did you do like when you woke up like that early?
The disease presentation, I just had to work on a presentation. I nailed it, by the way. But
That's good.
yeah.
That's so good.
I need I need
So
more
did you prepare the
time.
day of?
Kind of,
Oh my god.
but it's okay because it's all good. But I still have enough energy, and I kind of figured out like if I don't go on my bed, I'll be fine, and that's it.
Uh-huh.
Yeah,
Did
it's
you
my
take a
only
nap?
strategy. What?
Did you take a nap today?
Nope.
What? And you're running on 2 hours of sleep right now?
I still got work to do, so
No caffeine too?
no caffeine.
Oh my god. And you still have work to do?
Uh,
That's
yeah.
crazy.
I
I'm about to
mean,
go walk my dog.
walk your dog. It's like it's like 10:20.
Yeah.
Did you all right? You didn't pay attention to your dog all day.
Yeah, I didn't. I need to spend time with him now. Yeah.
Man, wait. So like 2 hours of sleep. What did you do in the morning?
I have club every Tuesday, Thursday morning. Um, so I woke up, brush my teeth, showered, eat breakfast, drive to campus 5:15, get there like 5:45, 5:50ish. Club 6 to 7, and then classes 7:30 to like 4 or 5, and then tutor, and then like eat, and then
Uh-huh.
office hours, and then now I'm here and I'm about to walk my dog.
I mean, let's see. Um, I'm just like thinking, just like because my brain's not working, I kind of forgot the first thing you said, kind of just like, all
Yeah.
right, but yeah.
Me too, me too. We're going crazy.
No, we're not. No, we're
Yeah.
not. It's all in
Yeah.
your head.
Yeah. Oh my god. Yeah.
Yeah. Things will get better. I mean, I only have like till Friday, and then I get to like sleep all day if I wanted to.
Yeah.
So
And then do you have a break, or like do you come back the week after?
yeah, we come back right after we finish or something. But
Oh shit.
yeah, I'm gonna use that time to like study, like for like not study, but like prepare myself more for AP laying because that's my sleep. That's like my sleeper class.
Mm-hmm.
I mean, because there's not a lot of work for it, but it's just mostly like writing, and I kind of need to improve my writing skills and see more big picture.
Yeah.
Yeah.
That's good.
What was the hardest thing you did today besides the sleep?
The hardest thing I did today was tutoring for 5 hours today.
5 hours. You tutored before? Wait, like at what time?
Like right after school on campus.
Ooh.
Because people scheduled it, and then I set my Calendly link, so they scheduled it right after my class time. So I did it on campus.
Hmm. Oh shoot, that must be
Yeah.
so rough.
Yeah. But I enjoy it. It's fun.
Uh, Fun in the sense that you don't get to do that every day. Like it's not like some 9 to 5. Like
Yeah.
yeah, more flexible. So yeah.
Mhm. Right.
Holy
Yeah.
2 hours of sleep. What time are you gonna go to sleep? Or like how long are you gonna sleep tonight?
I'm not sure. I took naps like during school, so I'm not like that tired. Yeah, so probably sleep late tonight too again. Because I have a
Hmm.
quiz this Friday I have to study for.
Uh, it's microbiology for me.
Yeah.
My average test scores are all 70s.
Shoot. You have microbiome test on Friday too? Me too, me too.
Yeah, but
Yeah.
it's a
Yours is
final.
the midterm, huh? Final, huh? Yeah.
Yeah.
Did you finish that study guide?
Yeah. 60%.
60%. Dang.
Yeah. I kind of realized I'm a little more lazy when I come home after school after being this tired. It's like,
Yeah.
yeah.
Let's
But
see.
it's just that I have so much like I don't know. It's well not time. I'm not burning time. I'm burning like my energy. Like yeah. All I need to do is like complete 75% of this thing. So
Mhm.
like and then, like I could just study like the rest of the notes that I have. Cause
Right.
yeah, I could like screen share right now.
Yeah, you
Like
can screen share.
microbiology stuff.
Uh-huh.
All right. So you can see my screen, right?
Yeah, I can see your screen.
Okay. So this is like our first quiz, you know, which of the
Uh-huh.
following is true? And then like this is the first thing that we learn since we're
Yeah.
dealing with chemicals. I got this wrong because I forgot to like put it is what actually how did I get that wrong? Actually, never mind. I can't think right now. But like I literally have it for all my quizzes and tests.
Oh my god.
Yeah.
Uh,
So I think I'll be good.
Yeah, review all those and you'll be good. That's good. You have a plan. Looks like you have a plan. A clear plan.
Very thorough anyway.
Yeah, that's good. Yeah, trust that plan and go with it, you know?
Yeah. These are all the questions. It's just that there's like the writing portion, but I feel like I shouldn't worry about the writing portion that much just because we went over it in class.
Right.
All I gotta do is recall,
Uh-huh.
which I'm having a trouble doing right now.
Yeah, your brain's tired. Can't
Mhm.
recall.
Hmm.
Yeah. Are you gonna come this Sunday, even though like you're done with
This
school?
Sunday, yeah, for sure.
Yeah, yeah. Like the study with me session and the
Yeah,
talking session.
yeah, the OG
Yeah.
study session.
Yeah. OG.
Uh, it's not that I'm in pain. It's just that like my brain feels like a certain way when it's hurt instead of like physical pain. I don't know how to describe it.
Uh-huh. It's like, is it like throbbing headache?
Not throbbing headaches. I never get headaches.
Oh, that's good.
It's just like my eyes.
Oh yeah, it's like closing, huh, by itself right now.
Yeah, just like their little slits now. Just like oh my god. Like I'm not like squinting. Like my eyes are relaxed, but they feel like they're just covering like almost a lot of my eyeball.
Oh shoot. But you have until like Thursday and Friday, right? You have like tomorrow, so you can sleep early now, wake up early,
Wednesday,
and like
Thursday,
fix.
Friday. Yeah,
Yeah.
that's true.
So
I got
you should.
Spanish. I got Spanish vocab, and I gotta memorize like, or like just like all the conjugations because I feel like Spanish was kind of a mistake, but I gotta take that class anyways. No problem anyway.
Oh, Spanish 2, 3, or
3.
3. Dang. So you took Spanish 1 in freshman, Spanish 2 sophomore.
Yeah, but like I also have a plan for that one. Let's see. It's mini. Oh yeah, mini study. Where is it? Yeah, here it is. I'm just gonna share my screen again.
Okay.
And boom. So I'm lucky since like this is our notes for like all Spanish and it's just like I don't know if you like you probably don't remember any of this anymore, but all the slides are here for all the notes and all the
Dang.
ch- changes.
Yeah, I never took Spanish. But is it like doable? Is it straightforward?
Yeah, straightforward. Yeah, just like also because written part is like worth more than like listening and what's the other part? Oh yeah, comprehension. Reading comprehension.
Yeah.
I even like took a picture of like the criteria for like how I'm supposed to meet like what was on the final. So it's just like a matter of like willpower. Like
Yeah.
how badly am I gonna study for this thing?
Right.
'Cause I got like actually like 2.5 days before that final.
Yeah. You should get some sleep tonight.
Nah,
Dang.
it's just mostly
Yeah.
vocab.
Uh-huh.
Yeah.
I'll be up and then I'll text you if you're still up later. But for now I'm gonna
What?
go
Like
on
through school or like do Discord?
Discord. Yeah.
Oh, okay.
Or do you want school? Through school.
Actually, Discord's better because
Uh-huh.
like I don't have Discord school on my phone.
Okay. Yeah.
Wait, why are you staying up? Oh yeah, gosh.
I'm studying
Friday.
for microbiome. Yeah. That's
Yeah.
on Friday. Before everything gets busy.
I mean, it's good that you're not putting it off, unlike me,
Yeah.
like during the start of this quarter. But I learned my mistake, but it's yeah.
Mhm. That's good. Yeah. Okay. I'll see you tomorrow, Ryan. It was nice catching up with you. And
Yeah,
then I'll see if you're still up tonight.
yeah, just like the slurred speech, just like
Yeah. We're so brain dead.
I I would not consider myself brain dead at the moment. I'd say that I have like 30% of my energy left in the tank.
Uh-huh.
30
I
to
see.
40. How
Uh-huh.
about you?
Like I could just keep going like, for like 60, 70 right now.
All
Because
right,
I took
man.
naps. That's why I took naps. You didn't take naps.
Hey, yeah.
Yeah.
If I took
Okay.
naps, I'd just sleep the whole time. It would 10 naps don't work for me.
Uh-huh. Dang. Okay. I'll see you, Ryan. I'll see you tomorrow
Yeah,
and later.
see ya,
Uh-huh.
goodbye. Or
Yeah.
like
Good
you could
night.
just text
Oh
me
yeah.
if you're way too like yeah,
Yeah.
3,
3, 2,
2,
1.
1.